Okay, I started recording.
Okay, so beginning live feed. Okay. Okay. Going live. Oh, error in the broadcast. Please try again. Okay. Let's start all over again.
Okay.
Okay. Got a bunch of stoppers upstairs. All right. One more time. It didn't stream. Forgive me, everyone. Just troubleshooting really fast so we get the live stream up.
Okay.
Okay, I'm in. Gonna hit the button. Does it look like the stream is going to work today? I'm going to give it one more chance.
Okay.
Okay. It appears like it's going live on Zoom, but then like the Facebook gives me an error.
Let me see.
But yeah, just have the page open on ours and see if it goes up or not.
Okay. Hold on a minute. I don't see anything.
All right.
Not that I don't know if anybody else can see anything if they've got their Facebook pages open. Does it say it's streaming right now?
It says it's preparing. All right. So it's getting a signal, the live feed. It looks good. And then when I go live, yeah, something's up with Facebook. We're not getting a live feed. We're 6 minutes in, Mary. I don't know if you want to just, we'll post a recording to YouTube and
Yes. Yeah, we'll do
carry
that.
on.
Sorry about that,
Okay.
Matt. But all right. Well, anyway, good evening, everyone. Then welcome to once again to AAI for our weekly Fridays at home. And AAI, as everybody knows, I think that it makes its home at William Miller Sperry Observatory in Cranford, New Jersey, on the campus of Union County College. And since the observatory is closed, we're doing these presentations online. So our presenter this evening is AAI member Max Watzky. Max is a member of AAI and has given presentations before. He will be a sophomore in high school in September. He has an interest in engineering, astronomy, and computer science. The title of his presentation is Starlink and SpaceX, the Future of Satellite Internet. So, Max, please begin.
Hi, everyone. My name is Max Watzky, and if you've ever been on a plane, you already know that satellite internet pretty much sucks. When you're high above the sky, out of range of cell towers and fiber optic cables, your only option is the airplane-provided satellite internet. It's really expensive, slow, laggy, and prone to disconnection. But all of that is about to change. Soon, a lot more people will be using a satellite internet. Cheap rockets and cutting-edge technology have put us on the cusp of a revolution, with the promise to change the web forever, and there is great risk and great reward for companies that are willing to enter the ring. Imagine a world in which networks of tens upon hundreds of thousands of satellites buzz overhead, providing some of the fastest internet ever seen all around the globe. A world in which a Zoom call is like being there in person. A world in which anyone can get access to fast internet, and a world in which you no longer have to pay United Airlines $29.99 to only check your email twice on a 4-hour flight. At the cutting edge of this revolution is the company SpaceX, which is embarking on an ambitious project called Starlink, which will redefine how satellite internet works in the modern era. Starlink is a collection of thousands of internet satellites that is currently being developed, with the end goal of delivering fast, reliable access to the internet in places underserved by traditional satellite internet companies. But why is SpaceX doing this? Well, to answer that question, we need to understand the history and motivations behind it and its founder. Over the course of the last several years, SpaceX has become a household name for their innovation in the world of private rocketry. They pioneered the technique of landing and reusing rocket boosters, developed the most powerful operational rocket in the world, the Falcon Heavy, help the country deliver American astronauts to the International Space Station for the first time since 2011, and launch more times per year than any of their competitors for some of the lowest prices on the market. However, recently, SpaceX has hit a revenue bottleneck. Demand for rocket companies to launch satellites into orbit is growing very slowly, while SpaceX's launch capabilities are growing rapidly, capping SpaceX's revenue at only $3 to $5 billion per year. That may sound like a lot, but in the eyes of Elon Musk, the eccentric billionaire founder and CEO of SpaceX, this is nowhere near enough. You may know Musk from SpaceX or for his role in the creation of the electric car company Tesla, or you might just know him from the news earlier this year that he named his son that. What's important to understand about Elon Musk is that he founded SpaceX with the end goal of rekindling public interest in spaceflight by eventually bringing humans to Mars. However, the SpaceX rocket that Musk intends on using in his Mars expeditions, this metallic beast called Starship, is still in the very early stages of planning and will require massive amounts of funding to develop, test, and produce. It certainly doesn't help that they have a tendency to explode. In order to get this funding, SpaceX intends to use its low-cost rocketry to expand into the telecom industry in the form of Starlink, which could bring in upwards of $30 billion per year once completed. This is a lofty goal for a company in the internet satellite industry, which has proved to be notoriously difficult for companies to enter. Large internet satellites are very expensive to develop and launch, costing tens of millions of dollars each. In addition, satellite internet has a bad reputation for being slow, especially when streaming live video, playing online games, or doing Zoom calls like these, which has made it difficult for satellite internet companies like Viasat to compete with land-based internet providers like Verizon or AT&T. In fact, the only places where satellite internet is viable at all are those where conventional internet access via cable is extremely slow, like rural or remote regions, and places where it's impossible to lay fiber optic cables, like on cruise ships in the middle of the ocean and on airplanes. In order for us to understand the way SpaceX is improving this industry, we need to understand the source of problems with satellite internet, the internet satellites themselves. The reason satellite internet exists in its current subpar form comes down to how conventional internet satellites operate and the challenges involved with managing their orbits. Let's say you're using satellite internet and you want to visit my amazing website, nebulousastronomy.com. You'll see it at the end slide. Great choice. The modem in your home would modulate or prepare the request for that website into packets of information encoded in binary, the basic language of computers. Then these packets are sent via radio waves from a dish on your roof to an orbiting internet satellite, which redirects your request to a ground station with access to the internet. Servers in the ground station would process the request, retrieve all the data associated with my website, like the words or images found on the homepage, and send it off to the satellite via radio. Finally, the satellite redirects that radio signal back to your dish, from which the signal can be demodulated into code your computer can read, and the website can be displayed on your screen. What's important to remember here is that essentially, internet satellites fulfill the role that would otherwise go to a cable in the ground, mediating between your device and the internet. The problems that come from satellite internet arise from problems in that kind of mediation. However, in order for an internet satellite to properly fulfill this role, there needs to be a clear line of sight between your dish and the satellite, and then between the satellite and the ground station. I don't know why my picture isn't loading there. In order to best manage this requirement, many different kinds of orbits have been considered for internet satellites. Many satellites, including the International Space Station and the Hubble Space Telescope, orbit Earth at a height that is less than 1,200 miles from the surface. Low orbiters like these don't have to travel very far to make it all the way around the planet, meaning that they can orbit Earth in only 1.5 or 2 hours, or about 16 times per day. However, this low orbit would come with disadvantages for conventional internet satellites. Traveling around the world so quickly means that satellites in low Earth orbit might only spend a few minutes per day over one particular place. Internet satellites might only need to service a small part of the Earth near a ground station like one country or region, but because one satellite might only have that region in its line of sight for a few minutes at a time, internet service would only be available for a short amount of time per day. In order to provide consistent internet service, you would need to put hundreds or thousands of satellites into a low orbit to always make sure one is overhead the serviced region. Keep that in mind for later. So, how do satellite internet providers get around this problem? In order to understand their solution, we got to dabble in some orbital mechanics. What you need to know is that objects fall along curved trajectories according to gravity, like in the case of this cannonball. The faster the object moves horizontally, the larger its curve can become. If you can accelerate an object to a fast enough speed, gravity will curve it downwards at the same rate that the object curves away from the spherical surface of the planet, and it will never hit the ground. That object has achieved orbit. The trajectory of an object's curve in orbit can be changed by accelerating or decelerating the object. For example, by adding more energy to an object in the form of velocity, that object will achieve a higher orbit. Even though objects traveling in higher orbits have more energy and travel faster than objects in lower orbits, they take longer to orbit the planet. So, some smart scientists use this principle to figure out that if you used enough energy to launch an object or a satellite into a circular orbit exactly 22,236 miles above the Earth's surface, it would take that object 23 hours, 56 minutes, and 4 seconds to orbit the planet, which happens to be the exact length of time it takes for Earth to rotate on its axis. A satellite orbiting at this height around the equator in a geostationary orbit would orbit at the exact same speed as the Earth rotates, meaning relative to the ground, it would stay over the same spot all day, every day, forever. Satellite internet companies put their satellites in geostationary orbits so that they can provide constant service to certain areas without having to launch hundreds or thousands of satellites. Now that we've gone over a little bit of how conventional satellite internet works, I think I owe you an explanation of how it differs from Starlink. Though Starlink is, at its core, made up of internet satellites, the way it operates is radically different from the satellite internet companies of old. At the core of Starlink's differences from these conventional internet satellite networks is the fact that instead of launching a few satellites into a high geostationary orbit, SpaceX plans on launching a lot of satellites into an extremely low orbit, about 341 miles above the surface. Remember how I said that satellite networks in low orbit need to have a lot of satellites to cover the whole planet? Well, SpaceX leans into this fact to an extreme. In contrast to the dozen or so satellites that other internet satellite companies might maintain, SpaceX will launch an enormous fleet of 12,000 satellites, which will then be increased to 42,000 over the following years, a feat that would be impossible for any of those other internet satellite companies. However, the reason SpaceX believes it can complete this task comes down to two main factors that set them apart from the rest. The first main factor is the design of their satellites. Traditional internet satellites are really big. For example, the internet satellite Viasat-1. Viasat-1 was launched in 2011 by the internet satellite company Viasat to provide internet service to rural regions over swaths of North America. Because this satellite has to service so many people over such a large area, it was built to provide an enormous amount of bandwidth. Bandwidth is a way of measuring the rate of transfer of information in the form of the binary language I mentioned earlier that computers read over the internet, and Viasat-1 can provide 140 gigabytes per second of bandwidth in total. For reference, if all of that bandwidth was concentrated to one computer, you could download the entirety of Wikipedia in less than a tenth of a second. However, split between the 40,000 or so people who use that satellite for internet access, each person is going to get very slow speeds. The ability to provide all of this bandwidth requires the satellite to contain a boatload of electronics and solar panels to keep its many antennas and dishes working 24/7. As a result, this satellite has a total weight of 8,050 pounds, which is about as heavy as a hippopotamus, and it ends up being an estimated 10 or 15 feet long, the size of a standard living room. In contrast, SpaceX's Starlink satellites are tiny. While one Viasat satellite might have to provide internet service for an enormous region all alone, when you have a fleet of 42,000 satellites in orbit like SpaceX, each one is going to be responsible for a very small area at a time. As a result, individual Starlink satellites will only provide about 20 gigabytes per second of bandwidth each, 1/7 the bandwidth of Viasat-1. Because of this lower bandwidth, nowhere near the amount of electronics and solar panels seen on the likes of Viasat-1 are needed to sustain Starlink satellites' operations. All in all, these Starlink satellites come in at around 500 pounds each, 1/16 the weight of Viasat-1 and about the weight of a small hippopotamus. While Viasat is the size of a living room, Starlink satellites are about the size of the kids' table at Thanksgiving dinner. This low weight and small size is important because, coupled with Starlink satellites' flat, compact design, it gives SpaceX the ability to launch more than one satellite in a rocket, compared to the Viasat satellites, which must be launched one at a time, which is a huge improvement in efficiency. This takes me nicely to the second main factor that sets SpaceX apart from the rest. They own the rockets that take their satellites into orbit. Using the example of Viasat-1 again, that satellite was launched using a Russian Proton rocket, which set back the makers of Viasat by $65 million, just for that one satellite to be sent to orbit. Ordinarily, SpaceX charges $62 million for launches of their flagship rocket, the Falcon 9, not that much less than the Proton rockets. But I would imagine that without the markup for profit, cost for one launch of the Falcon 9 is much less than $62 million, probably more like $30 to $40 million for all of the rocket components, labor, and fuel. In addition, this price can often be lowered even further by letting other companies hitch a ride on Starlink launches. This happened just last week, when 2 black sky imaging satellites were brought to orbit alongside Starlink satellites aboard a Falcon 9. However, instead of just launching one satellite for that kind of cost, SpaceX can launch 60 at a time. So, assuming SpaceX uses the Falcon 9 for all of their Starlink launches for the whole project at a cost of $20 million per launch, by my estimate, launch cost for Starlink could total $14 billion, not that far off from the official SpaceX estimate of about $10 billion. This may sound like a lot, but to show you how much of an improvement this is over the internet satellites of old, in order for Viasat to put a Starlink-sized fleet of Viasat-1s into orbit, it would cost about $2.7 trillion, which is about the same as the yearly GDP of India, or about the amount of money it would take to buy 3 bananas at Whole Foods. So, at least compared to many of its competitors, SpaceX has overcome the challenge of cost. However, many questions you might have about Starlink probably remain unanswered at this point. Chief among these kinds of questions is the question of how exactly Starlink satellites will work to provide internet. At their core, Starlink satellites will still have the job of mediation between a user and an internet ground station. The most important parts of these satellites are communication devices to transmit information and solar panels to power the satellite. However, their 341-mile low orbit introduces a big problem with Starlink satellites. Satellites in high geostationary orbits can have almost half of the entire Earth within their line of sight at a time. Meanwhile, satellites in a low orbit like Starlink have a direct line of sight to a far smaller area. In the case of Starlink, the satellite's small field of view means that most of them won't be able to communicate with the ground station directly at any given point, especially if there are only a few ground stations dotted around the world, which is most often the case. The solution here is to enable Starlink satellites to talk to one another. While one conventional internet satellite might be the only relay between the user and the ground station, a signal might end up having to travel between several Starlink satellites to get from a user to the ground station and then from the ground station back to a user. This interconnection is what makes Starlink a single project instead of a loose confederation of internet satellites. However, Starlink's dependence on its interconnection to operate creates an engineering challenge for SpaceX. Namely, what's the best way of sending information between Starlink satellites? First, let's look at the problems with the traditional option of radio waves. When thousands of satellites are all communicating with one another in orbit via radio waves, you end up with an enormous amount of interference, which can make it difficult for a radio receiver on one satellite to decipher the information being sent from another. This is because radio signals fan out in all directions instead of focusing towards one particular spot, which also ends up wasting energy by transmitting data in directions it doesn't need to go. SpaceX's solution to this problem is to use the most directionally sensitive method of communication possible for data transfer between Starlink satellites: super precise lasers. Every Starlink satellite will be outfitted with 4 lasers and receivers to send data to surrounding satellites. These lasers come with several advantages. Not only do they save energy by transmitting data efficiently, but they can also transmit data at a higher bandwidth than radio signals, which means faster download and upload speeds for users. Because of laser technology, Starlink could be able to deliver gigabit per second download speeds to customers, which is fast enough to download a 2-hour movie onto your computer in under a minute. Swapping out transfer of information via radio with transfer via laser helps bandwidth because the light waves that make up a laser beam have a much higher frequency than radio waves, which means that more information can be packed into a segment of a signal. However, lasers themselves come with problems. First, they can't be used for everything. You can imagine that there's some problems with shooting high-powered lasers towards people's houses, meaning Starlink satellites will still have to communicate with the ground using radio antennas. In addition, when a Starlink satellite wants to transmit data via laser to another satellite, it must point its laser extremely precisely to within only a few inches of the other satellite's receiver, which could be hundreds of miles away. Problems with laser pointing can be partially solved with some computer engineering, but aiming these kinds of lasers could remain a big problem nonetheless. Because of the challenges that remain with laser technology, Starlink satellites won't be launched with laser transmitters and receivers until late this year or maybe early next year. Now that we know how Starlink works differently from other internet satellite networks, we can start to tackle why it's faster. When I say faster or internet speed, I can mean 2 things: latency and bandwidth. We've already discussed a little bit how Starlink satellites' laser technology will improve bandwidth, but we haven't gone over latency yet. Latency is a word for the lag time between when data is sent and when it is received. For instance, the delay between when I go to the next slide and when you actually see that I've switched slides is called latency, and the delay happens because signals sent over the internet don't travel instantaneously. They are limited by the speed of light. In the case of data transfer to and from satellites in orbit, the main contributor to latency is the time it takes for a signal to physically travel through space. In this regard, Starlink satellites' orbital height of only 341 miles is a huge advantage compared to other internet satellites at 22,236 miles. This is because light in the form of radio waves only has to travel 1/70th the distance to get from the ground to a Starlink satellite than from the ground to a conventional internet satellite. In fact, it's this high latency involved with communicating with satellites in geostationary orbit that makes conventional satellite internet so slow and laggy, like what I described earlier. For example, let's say you in New Jersey want to send an email to your buddy in Chicago. If we were using conventional satellite internet, it would take about 230 milliseconds. A millisecond is 1,000th of a second for a radio signal traveling at the speed of light to reach an internet satellite 22,236 miles above Ohio from your home, and then another 230 milliseconds for the signal to get from the satellite to your friend in Chicago, for an absolute minimum latency of about half of a second. A half a second of latency doesn't sound too bad for an email, but it makes live video streaming or Zoom talk participation almost impossible. In comparison, it would theoretically take only about 5 or 6 milliseconds in total for a radio signal to get from your home radio dish to a Starlink satellite, and then from that Starlink satellite to your friend's apartment in Chicago, an enormous latency improvement over conventional satellite internet. And this even edges out the fiber optic cables that link Chicago and New York, which would take about 16 milliseconds to transfer that email, about 3 times slower. Even though the data is traveling a shorter distance through that fiber optic cable than it would via a Starlink satellite, light travels faster through space than it does through the glass in fiber optic cables, making fiber optic slower than Starlink in terms of latency. So, with its improvements in bandwidth, latency, and with thousands of satellites providing coverage all around the world, Starlink will be in a prime position to pick up where conventional satellite internet left off. Of course, this means capitalizing off of rural areas with no better options, but it also puts Starlink into a unique position to dramatically increase access to information and thus opportunity to the poorest and most remote people on the planet, like those in sub-Saharan Africa who have been traditionally completely ignored by all internet providers, even satellite internet providers. However, Starlink probably won't work too well for people like you, who live in a denser suburban or urban areas that might already have decent internet options. Let's get into some of the numbers on that. Because Starlink satellites are in a low orbit, traveling around the Earth many times per day, it's impossible to concentrate many satellites over densely populated urban areas. Individual Starlink satellites only provide 20 gigabytes per second of download speed each, meaning in order to provide the advertised speed of 1 gigabit per second for all customers, each satellite could only provide internet for 160 people at a time. Now, I doubt everyone using Starlink will be using the maximum download or upload speed, meaning 160 is the bare minimum amount of people that can use a Starlink satellite at a time. But this still goes to show that very few people, maybe 1 in 100 at best in major cities or metropolitan areas like New York metropolitan area, would be able to use Starlink effectively. SpaceX will sell Starlink internet plans for about $80 per month for gigabit per second download speeds, plus another $100 to $300 up front to purchase a small radio dish to communicate with Starlink satellites. A pretty great price compared to the $100 per month or so charged by conventional satellite internet providers like Viasat that might provide only 1/10 the download speed. However, SpaceX might end up selling Starlink access at slightly slower speeds for cheaper to those in developing nations that might need access to faster internet but lack the money that those in developed nations would be able to pay. Let's say that on average, SpaceX charges $50 per month per customer and 300 people can get Starlink internet access at a time from each satellite, and SpaceX has 42,000 satellites in orbit, their final planned amount. That alone would generate over $7.5 billion per year, which is not too far off from what most satellite internet companies would expect in yearly revenue. Now, wait a second, I hear you asking right now, didn't I say a while ago that SpaceX projects it can make $30 billion per year off of this? Where is the extra money going to come from? Well, it turns out that there is an enormous untapped market for extremely low latency internet, the financial sector. Remember when I was talking about the options for internet communication between New York and Chicago? Well, it turns out that most stock trading in the US goes on in New York, and most trading in futures goes on in Chicago. For our purposes, though, we can sort of treat futures and stocks as the same thing. Stock traders in New York are looking for risk-free ways to make money. However, these days, the New York Stock Exchange is really just a TV set. The real action is going on in the basement, where super fast, super expensive computers do all of the stock trading. A fiber optic cable connects these computers to the futures market in Chicago so that when prices for stocks change in New York, the prices can be updated in the Chicago market in a matter of about 16 milliseconds, the time it takes for data to physically travel through that fiber optic cable I talked about. For example, let's say you are trading an Apple stock, and the price in New York and in Chicago for one share of Apple opens at $100. After the market opens, the price on the New York Stock Exchange goes up to $100.01. But for that 16 milliseconds of latency time, the computers in the market in Chicago still think that the price is just $100. So if you can find out that the price has changed in a shorter time than 16 milliseconds, your fancy computer can quickly buy an Apple future for $100 in Chicago and then sell it for $100.01 in New York for a risk-free way of making 1 cent. However, repeat this thousands or millions of times per day every time the stock price changes with thousands of stocks, and you're looking at incredible amounts of profit. There's already been a huge push to find the fastest possible way to transmit data from New York to Chicago for this purpose. In fact, a group of hedge fund managers hired the company's Spread Networks to build a new $300 million fiber optic cable directly from New York to Chicago to reduce the amount of time it takes to transfer information between the cities from 16 milliseconds to 13 milliseconds, just a 3 millisecond difference. Because Starlink could achieve extremely low latencies for information transfer between New York and Chicago as low as 5 or 6 milliseconds, it's perfect for this kind of purpose. And we know from the $300 million price tag on that fiber optic cable that stock traders are willing to spend whatever it takes for low latencies so they can game the system. Selling special ultra-low latency Starlink connections at high prices for stock traders, not just those in New York and Chicago, but in financial centers all over the world, are probably where most of SpaceX's expected $30 billion in revenue is going to come from. At this point, I've told you a lot of what you need to know about Starlink, including how it works, why it matters, how much it costs, and why SpaceX is building it. But one of the big questions still remains. When will Starlink internet service be available to the public? Well, to date, over 500 Starlink satellites have been put into orbit, and beta testing of Starlink internet is planned to begin this month. If you want to be a beta tester, you can sign up for email updates on the Starlink website, although please don't hold me accountable if they decide to send you a bunch of spam. Following this initial stage of testing, Starlink should become available for the public in the US and Canada starting late this year, and will be rolled out to the rest of the world over the course of the next couple of years as more and more satellites go into orbit. It's kind of amazing how quickly SpaceX has been able to do this, going from no internet satellite infrastructure at all when the project was formalized in 2015 to beginning internet service this year with hundreds of satellites already in orbit and thousands more on the way. This can be attributed to SpaceX's launch efficiency, bringing 60 satellites to orbit at once, and their incredible launch frequency, sometimes launching several times each month. At this rate, the preliminary constellation of 12,000 satellites could be done in a matter of only a few years. However, this breakneck pace has alarmed many scientists and amateur astronomers who have some concerns about the negative consequences of Starlink. One major concern is space junk. According to the Union of Concerned Scientists, as of August 1st, there are 2,666 satellites in orbit around the Earth right now. Now, there's probably more, but the government doesn't want to tell us about them. By increasing that number of satellites by 12 to 42,000 over the next several years and decades, Starlink is increasing the risk that any two satellites will collide in orbit. This has happened before, and when satellites collide at thousands of miles per hour in space, they can create tens or hundreds of thousands of pieces of space debris. When these pieces of debris float off into orbit, they could set off a chain reaction of destruction, as pieces of debris collide with satellites, creating more debris that could then collide with more satellites, creating more debris, in a vicious cycle known as Kessler syndrome. If you've ever seen the 2013 movie Gravity, you'll know that a minefield of space debris in orbit could pose a serious risk to humanity, crippling the satellite networks that we rely on for internet or weather, and preventing us from launching any rockets into space. In response to some concerns about space junk, SpaceX has taken many precautions with Starlink. For one, the low height of Starlink satellites, 341 miles, means that their orbits will naturally decay over the course of a very short period of time, only a few years, and then the satellites will fall back to Earth. Though this means SpaceX will constantly have to replace their satellites, it also means that any space debris created by collisions of Starlink satellites will also decay very quickly and fall back to Earth. Don't worry, I'll be handing out hard hats at the end of this presentation. The reason this happens is because at 341 miles, though the atmosphere is extremely thin, there are still enough air molecules to slow down orbiting objects when they come in contact with the air, lowering the object's orbits, which causes them to run into even thicker air, speeding up the cycle of decay. In addition to this failsafe, Starlink satellites are equipped with a database of all known satellites and pieces of space debris and a small special rocket engine called an ion thruster that can be used to avoid these objects if they come on a Starlink satellite's path. However, Starlink poses another danger, one less potentially catastrophic than space debris, but more relevant to us at Sperry Observatory. If you've ever taken long exposure images of space with a camera or a telescope, you know that it's incredibly frustrating when a satellite goes by your field of view. They can be really, really bright and often ruin the image or the data you're taking. And this isn't a problem exclusive to amateur astronomers. Satellite interference also disrupts the work of professional astronomers, who are often dealing with incredibly sensitive equipment and whose important scientific data can be completely ruined by a passing satellite. With the addition of thousands of new satellites into orbit, satellite sightings could go from pretty rare to happening all the time, which could seriously hinder astronomers' ability to do research and take pretty pictures going forward. SpaceX has attempted to fix this problem, with some limited success. They tried painting all the reflective surfaces on the satellites black, which made it harder for them to be detected in visible light, but the Starlink satellites still proved to be an annoyance in the infrared or heat spectrum. Now, SpaceX has begun installing special visors on the satellites to prevent excess heating, and they have even made it so that Starlink solar panels can rotate independently of the satellite so that they never reflect light towards the ground. However, with the first batch of these satellites being launched just a couple months ago, we don't really know yet if the visors actually work or not. Though SpaceX has been receptive to scientists' concerns on these two issues, it's hard to tell if other companies will care just as much. After all, it's not just SpaceX with ambitions of mega constellations of satellites. OneWeb and Amazon, yes, that Amazon, also hope to get in on the action with networks of their own. After all, with huge markets for internet all around the world and enormous amounts of interest from the financial sector, the satellite internet networks of the future have huge potential for profit. As more companies enter the ring with competing interests, an ever ruthless drive for profit, and perhaps less concern for real problems that could affect astronomers and the world, I would encourage you to be vigilant. Though the privatization of space has been picking up steam for decades now, the rise of ultra-profitable networks of internet satellites could mark the beginning of a new era, with the control of space not falling into the hands of cautious but sometimes ineffective governments, but to ruthless and efficient corporations. Go ahead, buy your Starlink internet plan if you want. But we all must make sure to stay cautious and encourage our government and the governments of the world to ensure that space remains a place for everyone, not the select few, and to see to it that regulations are put in place so that the concerns of astronomers and everyday people alike will not be swept aside by the private sector, even in the pursuit of progress. Or not. That's your call. Just make sure to wear your hard hat. All right. Thank you so much for taking the time to listen to me today. I did my best to cover as much as I could in the most straightforward way possible. But I'm sure there's plenty of questions you might still have. You can ask me now, or you can reach out to me over email via the contact section of my website, nebulousastronomy.com. Thank you so much.
All right, Max. That was a great talk. Thanks for that. We do have some questions.
All right.
Isabel submitted, I'm thinking that this amount of satellites near to the Earth's surface will be greatly affect ground-based astronomical observations.
Yeah, that's right on. I was just last year, I was at an astronomy program out in Arizona, and we were lucky enough to have some guests come in, and some of our counselors who have lots of experience with professional astronomy and astronomy as a science, and they were complaining a lot actually about the number of satellites that they've been seeing recently, and how it's really concerning for them that more satellites are going to be going up in the future, especially in the volume that we're going to be seeing with Starlink, because it can seriously interfere with their observations.
Great, thank you. Okay, Bob Ruggiero asks, what connection, if any, does this compare to 5G? Any connection between the two?
So I would say this is going to be pretty similar speed to 5G. Actually, it's very, very fast internet. But I don't think this is related to 5G. I think it's more of it's this is something you'd be using for Wi-Fi, not necessarily for cell service.
Steve Clark posts, this sounds like a boon for RVers who now rely on RV park or campground Wi-Fi which is not very reliable at most sites. Same with internet over cell service. Again, spotty in places, especially those who are boondocking in remote areas where neither Wi-Fi nor cell service is available.
That's totally right. Yeah. It could be great for our viewers because, you could get pretty amazing internet speeds out in the middle of nowhere as long as you're willing to bring your internet dish with you. And SpaceX has said that they're trying to make them portable so that people can stick them on cars and RVs. Um,
Dennis Conti writes, what is Starlink's redundancy plan to cover individual satellite failures?
That's a great question. So the sheer number of satellites that are going up is in itself a plan to create redundancy. They could lose a lot of satellites at a time and still have the network going because at any given time there's always going to be more than one satellite overhead, and they're going to be continually launching satellites anyway because of the speed at which their orbits decay.
Great, thanks. Stephen Cosmo writes, any comments regarding RFI interference with radio telescopes? Example, ALMA.
This is a pretty big concern. This is part of the reason why they're using laser technology. I didn't mention it earlier, but the radio wavelengths can also be relevant to astronomers who are looking for who are looking at other objects in space using radio waves, and that's one thing they're doing. But I could also imagine the radio signals that they're beaming to and from Earth to also be a problem, although they're probably going to be keeping them to one specific wavelength, which should be pretty easy for radio astronomers to cut out if they see it. They already have to deal with the internet satellites that we already have and cell towers and whatnot.
All right. Cliff Ashcraft posts, excellent presentation, Max.
Thank you, Cliff. I really appreciate it.
Frank posts, can balloons compete?
I'm pretty sure to put the 500 pounds worth of equipment on the balloon, it might weigh it down a bit too much, but so long as you're willing to put a lot of balloons up there, I think you could do something similar.
Jeremy Carlo writes, great talk. What sort of antenna would a customer need? You mentioned a dish, but if the satellites are low Earth orbiting, they're moving quickly, so a dish would have to slew. Would an omnidirectional antenna be used instead?
So they are using omnidirectional dishes for this purpose. They should work as long as a satellite is above 20 degrees above the horizon or so. Yes.
Great. Stephen writes, how about Starlink sats falling to Earth that will not disintegrate, interfering with air travel?
So you make a good point about the disintegration. Actually, the hard hats are probably not necessary, but I would assume that they're so small and light, and they're not made of any materials that are meant to withstand orbital heat. Sorry, re-entry heat. So when they hit the atmosphere and burn up, I'm pretty sure they won't become a problem anymore. They'll just completely disintegrate.
John Konzimbo writes, how does Starlink plan to move replacement satellites into gaps that can be far apart?
This is a really interesting question. It has to do with how they get satellites into their correct places in the first place. Um, they use those ion thrusters I was talking about. They're really super efficient rocket engines to slowly get Starlink satellites into the right inclination, which is sort of the angle that they rotate around the Earth, and the height. And so what SpaceX is doing is, for redundancy, they're putting them at that 341-mile level, and then later on they're going to put some in higher levels to create even more redundancy. Although the 341-mile orbit seems to be what they're sticking with. In terms of filling the gaps, it should be pretty easy using those ion thrusters if they need to fill a gap immediately, although they can always launch some more satellites up there in the longer term. Excuse me.
All right, Steve Clark adds, RVs have omnidirectional antennas available now for satellite TV reception, DirecTV, etc. And great talk.
Thank you so much. Yeah. Um, yeah.
Brian Lemley, he says, how will this affect launches through the 341-mile orbit?
So this is actually a really good question, and I haven't seen that much writing on this question, but I would assume that it would be not too difficult to avoid the satellites because they're very, very small, and they're generally a couple hundred miles apart. I assume, and if there's a real emergency where they're about to come in contact with each other, the rocket could maneuver around the Starlink satellite, or the Starlink satellite could maneuver out of the way using one of those little rocket engines.
Right. And with that concludes all our questions. We do have one comment from Charlie Rule in the chat, and he says, "Excellent presentation, Max." Oh,
Oh, thank you.
we've got a stream. We've got a stream of comments coming in on the Q&A. Let me just read them out to you real quick. Mark Stabinsky, will this put Verizon out of business?
That's a good question. So at the moment, probably not, because the whole point of Verizon is that you don't need to lug around a big radio antenna wherever you go. But I could imagine as time goes on, radio antennas getting smaller and smaller, so that you could probably, have one built into your phone in 20 or 30 years, which might very well put Verizon out of business.
Bob Ruggiero writes, great speech. Are you sure you are only in high school?
Thank you. I appreciate it. I am in high school.
Excellent. All right. Now that concludes all open questions. Grace says, good job, Max.
Thank you, Grace.
All right. With that, Mary, I'll turn it over to you.
Okay, I just want to thank you again, Max. It was an excellent presentation, really informative, very interesting. Just want to remind everybody, join us every Friday night at 8 p.m. online. Our presentation next week is Ice Giants, Uranus and Neptune by AAI member Dr. John Sickle. And we are planning to stream that live on AAI's Facebook page. And with that, thank you for joining us tonight and wishing everyone clear skies.